Hello, everyone. My name is Stampino-Strain, and today I will be presenting my Math 101 final project. So I decided to name my project Euclid, nope, Furstenberg, because I will be proving the infinitude of primes using a proof developed by Furstenberg in 1955. So let's get started. Now we're going to begin with a little bit of introduction in history. And we're going to start by saying that Euclid developed the most famous proof for the infinitude of primes in his work Elements in 300 BC. Now, someone else who developed a proof for the infinitude of primes is this guy named Furstenberg, and he developed this proof as an undergraduate student in 1955. Now, although Euclid's proof is definitely more famous than Furstenberg's, I will be focusing on Furstenberg's proof for the remainder of this presentation because he uses a very exotic topological space that I found very fascinating. So let's get started. We're going to begin by brushing up on a few definitions. And the first one being, what is a topology, right? So we let X be a non-empty set and let T be a family of subsets of X. We say that T is a topology on X if the following three conditions are satisfied. The first, both the empty set and X are elements of the topology T. The second, any union of arbitrarily many elements of the topology T is an element of T. And the third, any intersection of finitely many elements of T is also an element of T. And now we can define a topological space, and we say that if T is a topology on X, then X together with T is called a topological space. And now it's also important to note that the elements of T are called open with respect to the topology. All right, so with this in mind, let's kind of get started with the ideas we're going to be working with. So our topology of concern is going to regard something called the arithmetic progression, right? And so again, in this proof, we're going to define a topology on the integers using this arithmetic progression, and it's defined as follows. Now, this is not very intuitive, so if you need to spend a little more time thinking about that, feel free. But essentially, an arithmetic progression has the following construction for given values of n and k, or where n and k are both integers, right? So we can say it's read AP n k equals the set of all k plus a times n such that a is an integer, right? And so to better understand arithmetic progression, because this is rather, I don't know, non-intuitive, I guess, definition, let's observe three distinct examples in which 47 is an element of our arithmetic progression. So let's begin with example 1. So we let n equal 5 and let k equal 2, so that way we get AP52, which is defined as follows. So it's this set right here. We let n equal 4 and k equal 3 in our second example, so that AP43 is defined as follows. It's this set right here. Now, in example 3, we let n equal 10 and we let k equal 7, so that AP107 is defined as follows. And it's this set right here, right? So it's very important to keep this in mind as we move forward. Now, we're going to show these examples in a visual sense to maybe give people a better idea of what we're dealing with. And we can express them, we can showcase these examples visually using a number line. So our first example, example 1, we have AP52, and it's conveyed with this number line. It's important to note that AP52 is an infinite set. It's just that I don't have infinite space on my screen, so I wasn't able to show this the whole set, but I was able to show from everything between -20 and 50. And that's the case for the second example as well, AP43, and the third example as well, AP107. So let's continue moving forward, and let's finally define our topology on the integers, right? So we call this the arithmetic progression topology. And we let Z be our non-empty set, and we let T be a family of subsets of Z. And we define T, our arithmetic progression topology, as follows. We define T as a set of sets where U is an element, or a set of sets U, where U is an element of the integers, where U is open if and only if it is either a union of arithmetic progressions, if it is an arithmetic progression itself, or if it is the empty set. In other words, U is open if and only if, for every x in U, there is some y that's not equal 0, such that AP yx is an element of U, and U is an element of T. So that's our topology. And now let's double check if T, or we claim that that is our topology. Now let's double check that T is actually a topology, right? So using our definition of a topology before, let's check that the following three conditions are satisfied to assert that a proposed arithmetic progression topology T is in fact a topology on Z. So the first condition we have to check is that both the empty set and Z are elements of T. The second condition is that any union of arbitrarily many elements of T is an element of T. And the third is that any intersection of finitely many elements of T is an element of T. So let's begin by asserting the first condition. So our assertion of 1 begins with answering this question: is the empty set an element of T? And we notice that yes, by our definition of the topology, the empty set is an element of T and it's open. The second question we have to answer is the set of integers an element of T? And yes, we notice that the set of integers can simply be defined as AP10, so AP10 equals a set of all integers via arithmetic progression. So Z is an element of our topology and therefore must be open. So our first condition is satisfied. We can put a little check right by that. So our second one is a little bit more complicated, and it states that the second condition we have to satisfy is a little bit more complicated. So we have to show that any union of arbitrarily many elements of T is also an element of T, right? So to assert that number 2 is true, well, we define a set L to be the union of arbitrarily many elements of T. So it is the union of arbitrarily many sets U in T, right? Therefore, we can define L mathematically as follows, right? And so with this definition of L, our goal is to show that regardless of the value of I, and therefore the amount of open sets Ui in the union, remember, because we're considering the union of arbitrarily many elements of T, we can say that L is an element of our topology T. Very important. So let's consider an arbitrary value B such that B is an element of L, right? By our definition of L, this means that B is an element of Ui for some I, right? Now, remember that our definition of the arithmetic progression topology says that Ui is an element of T if and only if, among other things, it is a union of arithmetic progressions AP and K, where AP is defined as such, right? Therefore, if B is an element of Ui for some I, then B is an element of some arithmetic progression, which is a subset of Ui. In other words, there must be some arithmetic progression in Ui of which B is an element if B is an element of Ui, right? So let's list our relevant knowledge thus far. The first piece of relevant knowledge is that if B, that's an element of Ui, or if B is an element of Ui for some I, then B is an element of some arithmetic progression NB that's a subset of Ui for some n greater than or equal to 1. Our second piece of relevant knowledge is that our arithmetic topology or arithmetic progression topology T is defined as the family of subsets of integers that contains all arithmetic progressions and their unions. The last bit of relevant knowledge is that L is a union of arbitrarily many elements of T. We define that mathematically. Now, given the statement made in A, we know that AP and B is an element or is a subset of L for some B element of Ui and some n greater than or equal to 1. This is because AP and B is an element of Ui and L is, again, a union of arbitrarily many elements of T, right? So thus, L is an element of T since for any B that's in L, AP and B, the arithmetic progression of n and B, is a subset of L. And given the statements made in B, T contains all arithmetic progressions and their unions, right? So in conclusion, any union of arbitrarily many elements of T is an element of T because, given C, L is a union of arbitrarily many elements of T, and L is an element in T. Now, that was definitely a mouthful, but we've shown that any union of arbitrarily many elements of T is an element of T for our arithmetic progression topology. So we can put a little check mark next assertion number 2. All right. And so now we have to check that our last condition is true, and our last condition being any intersection of finitely many elements of T is an element of T. So let's get started with that, right? So to begin, let's define a set M to be the intersection of finitely many elements of T. So it's the intersection of a finite number of open sets U element of T. Therefore, we can define M mathematically as follows. With this definition of M, our goals show that regardless of the value of K, and therefore the finite number of open sets Ui in the intersection, M is an element of our topology T. Right? So given that our goal is to show that any intersection of finitely many elements of T is an element of T, we will consider an example to convey a pattern and then generalize that pattern to our finite value of K sets in the intersection. So let's begin with this example. For example, for our example, let us consider U1 and U2, where U1 equals AP43 and U2 equals AP107, and U1 and U2 are elements of our arithmetic topology T, right? And that makes sense because we defined our arithmetic progression topology to contain all arithmetic topologies, or all arithmetic progressions, sorry. So from our previous slides, we recall that AP43 is defined as follows, right? It's this set, and visually, it's defined like this. And we also recall that AP107 is defined as this set, and visually, it looks like this on the number line. So we say that the intersection of U1 and U2 is defined as the following in this case, right? So the intersection of U1 and U2 is this set, and visually it looks like this on the number line. So after some consideration, we notice that U1 intersect U2 is equal to AP20, 7, right? Thus, because we defined U1 as AP43 and U2 as AP107, the intersection of the two equals AP20, 7, right? So let this sink in for a little second, but this is a very, very important pattern that we're noticing because we can claim the following. So let's bring it all together to make a rather nuanced claim. Once again, we calculated that AP43 intersect AP107 is equal to the arithmetic progression of 20 and 7. We notice that 20 is the least common multiple of 4 and 10, which, when written mathematically, is LCM 410 equals 20. So we use this information to make the following claim. So for any two arithmetic progressions, I'll call them APN1, K1, and APN2, K2, the intersection of these two arithmetic progressions is equal to the arithmetic progression of the least common multiple of n1 and 2, and z, where z is some integer. We're not really sure what this integer is, but we can make this claim, and we know that z is some integer, and we know that our arithmetic progression in the first bit is the least common multiple of n1 and n2. Therefore, we say that our claim is generalizable across any number of finite arithmetic progressions, implying that the following is true. So the finite union, or the union of finitely many arithmetic progressions, ni, ki, all the way up to j, is equal to the arithmetic progression where we have n is equal to the least common multiple of all n's up to nj, and z is some integer, right? So with this, it follows that this arithmetic progression that we define with this least common multiple is a subset, right? Or is essentially equal to this union of finitely many arithmetic progressions, right? Now, with our claim in mind, let's finalize our assertion that any intersection of finitely many elements of T is also an element of T. So again, let's recall how we defined M to be the intersection of finitely many elements of T, where each UI is an open set in T, right? Now, assume without loss of generality that M does not equal the empty set, right? So there is some overlap between these unions, or between these UIs, these elements of T. Remember, we define each UI to be an open set in T that is one of two things. It's either an arithmetic progression or it's the union of multiple arithmetic progressions. In either case, whether it's an arithmetic progression or the union of multiple arithmetic progressions, it follows that m is equal to some arithmetic progression where are in the first place we have the least common multiple of n1 all the way up to nk, and z, where z is some integer given our claim. Now, it is essential to recall that our topology T is a family of sets of open sets U that include all possible arithmetic progressions. We have just defined M to be an arithmetic progression itself, so it follows that M must be an element of T as well, right? And this is all deriving from the claim that we made. Therefore, because M is the intersection of all UIs, or the finite intersection of all UIs, where each UI is an element of T, right, an open set in T, it must be true that any intersection of finitely many elements of T is an element of T. So we can put a check mark by our third condition, and so we've shown that T is indeed a topology on the integers Z, right? Because the arithmetic progression topology T satisfied all three conditions of what a topology is. So now that we've done that, let's move forward and make two essential observations about our topology, right? These observations are very, very important. So again, spend some extra time maybe thinking about this if need be, because these are very, very essential to our proof. So again, we're now ready to begin our proof, but we need to make these observations. The first observation is that if A subset of the integers is open, then A is either the empty set or the cardinality of A is infinity. The second observation is that every arithmetic progression A, P, and K is both open and closed in the integers. So now we're going to focus on showing why the first observation is true. So our claim is that if A subset of the integers is open, then A is either the empty set or the cardinality of A is infinite. First, let's consider why this holds true under our topology for when A is the empty set. This is because we define our topology as such. So A could be the empty set when A is open, right? We define our topology as such. We say that our topology T includes the empty set, and we say that the empty set is open. So if the empty set is open, if A is open, then A could be the empty set. Next, let's consider why this holds true under our topology for when the cardinality of A is infinite, right? This is because in this case, A is non-empty and open, and every non-empty open subset of the integers under our topology contains an arithmetic progression, which by definition is infinite, right? So in this case, if A is non-empty and open, then by definition, A is infinite because every non-empty open subset of the integers under our topology contains an arithmetic progression, and this arithmetic progression is infinite by definition. Thus, our claim holds true, right? So our first observation, we just show that it's true, so we can put a little check mark next to that. And so for our second observation, we have to show that every arithmetic progression, A, P, and K, is both open and closed in the integers, right? So let's show that this is true. So our claim again is that every arithmetic progression A, P, and K is both open and closed in the integers, right? So first, let's show that A, P, and K is open. Again, by the definition of our topology T, our arithmetic progression topology T, A, P, and K is open since T is a family of open sets U, in which U is either a union of arithmetic progressions or an arithmetic progression itself, right? So by definition of our topology, A, P, and K is open. Now, we want to show that A, P, and K is closed. Now, given our definition of closedness, in other words, we want to show that the complement of A, P, and K is open, right? So let's do this again by considering an example. Make our lives a little bit easier and make this a little bit more digestible, right? So let's consider the arithmetic progression AP52 as our example, something we've mentioned previously. So the complement of this set is the finite union of all arithmetic progressions AP5R, such that R is an integer between 0 and 4, and R is not congruent to 2 mod 5, right? So in other words, the complement of AP52 is the following. Or in other words, it's the union of AP50, AP51, AP53, and AP54, right? That's what the complement is equal to. Evidently, the complement of an open arithmetic progression set can be written as the union of other open arithmetic progression sets. And this result can be generalized to all arithmetic progressions, right? So this is very, very important to recognize that the complement of any AP is the union of other APs. Very, very, very important. So to generalize this, we claim that the complement of an open arithmetic progression set, AP and K, is the following, right? Is defined as this, where I begins iterating at 0, right? Therefore, the complement of an arbitrary open arithmetic progression set, AP and K, is the finite union of other open arithmetic progression sets. Since we know that the finite union of open sets is open, we can claim that the complement of an arbitrary open arithmetic progression set, AP and K, is open. So the set AP and K must be closed, right? If the complement of something is open, then that something itself must be closed. And this is exactly the case for AP and K. Therefore, we've shown that AP and K is open, right? And we've shown that AP and K is closed by showing that the complement of AP and K is open. Now, this is sometimes when we consider topologies, it's definitely a mouthful and kind of a lot to digest. But definitely take a moment to think about this and understand that AP and K is both open and closed in Z under our topology. Thus, we have successfully shown that our second observation holds true. Right? So we can put a little bit check mark right next to that and move forward. So finally, let's get to our proof, right? We've really set the foundation for what this proof consists of, and now let's get to it. So again, throughout this proof, we must recall the two observations to ensure that we follow along consistently, right? So the two observations are the two that we just established, but again, we'll read them out loud. So if A is a subset of the integers and it's open, then A is either the empty set or the cardinality of A is infinite. That's the first observation. And the second one is that every arithmetic progression, AP and K, is both open and closed in the integers. So we begin this proof by defining the set of all prime numbers to be Q. Now, let's consider the set P, which is the union of arithmetic progressions over prime numbers, right? So it's P equals the union of AP P0, where P is an element of Q, or P is a prime number, right? So again, we're considering these two observations, and our claim is that there's an infinite number of prime numbers, right? And so let's begin our proof. We begin by assuming that there are a finite number of prime numbers, right? So obviously, this is going to use a proof by contradiction. So we assume that there's a finite number of prime numbers, and given our prior notation, this means that we assume the following. We assume that the cardinality of Q, which is our set of prime numbers, is less than infinity, right? It's finite. Once again, we define a set P as follows, right? It's the union of all arithmetic progression of prime numbers, where P, again, is an element of Q because P is a prime number. And so it is also true, it's also important to remember that -1 and +1 are not considered to be primes. So along with our first definition of P, we can rewrite P as follows, given that every other integer has a prime factor. So P is essentially the set of all integers without -1 and +1, right? So now, given that the cardinality of Q is less than infinity, right? Or that we're considering that there are a finite number of prime numbers, P is a finite unit of closed sets given since we are working under the assumption that there are finitely many primes, right? So P is a finite unit or union of closed sets, right? Now, because the finite union of closed sets is closed, and every AP and K is closed by our definition made in the second observation, P must also be closed, right? So we're defining our set of the union of arithmetic progressions were with prime numbers to be closed, right? Because A, P, and K, again, by our definition in the second observation, is closed, and the finite union of closed sets is closed. So P must be closed as well. Now, since P is closed, we know that by definition, the complement of P is open, right? So taking into consideration that P is also defined as the set of integers without -1 and +1, the complement of P is the following, right? The complement of P is -1 and +1, the set of -1 and +1, right? And so, again, because P is closed, the complement of P is open. So -1, +1 must be open, right? Under our assumption that there are finitely many primes. So given our first observation under the topology T, the arithmetic progression topology T, we know that if a set A, which is a subset of the integers, is open, then A is either the empty set or the cardinality of A is infinite, right? However, we know that the following two things are true. First of all, the set of -1, +1 is not the empty set, right? It's not equal to the empty set. And we know that the cardinality of the set -1, +1 is 2, which is not equal to infinity, right? So therefore, the fact that we derived that -1, +1 is an open set is a contradiction of our first observation, right? Because we're claiming that -1, +1 is an open set, but we know that if a set is open under our topology, then A is either the empty set or the cardinality of A is infinite, right? But in this case, we're saying that -1, +1 is open, and that's just impossible, right? That's where the contradiction lies. So now, since the contradiction that -1, +1 is an open set was derived under the assumption that there are finitely many primes, and therefore P is closed, right? Because the finite union of closed sets is closed, right? And we're saying that the AP P0, that union is closed, which is P. It must be true that there are infinitely many primes, right? Again, this is very important, so I'm going to repeat it. Now, since the contradiction that -1, +1 is an open set was derived under the assumption that there are finitely many primes, it must be true that there are infinitely many primes. Therefore, by way of contradiction, there must be an infinite number of prime numbers. Crazy. So that concludes our proof, and that concludes my presentation. Because we've successfully shown, by way of contradiction, that there are an infinite number of prime numbers. Now, I wanted to list a few works cited. There was this really, really helpful article that I found on this proof by Keith Conrad. And I also used the book that Professor Corrali assigned to us a lot to define like topology and topological spaces throughout this. And I wanted to also give a huge, huge, huge thank you to Professor De Silva in Pomona College's math department for his guidance with this project as well. He helped me out a ton, so I really appreciate that. And I just wanted to end by saying thank you for watching, and I hope you enjoy it. I hope you learned something new. And if there are any questions, feel free to email me about it if there are. And I would love to hear any feedback that y'all have to give. It was honestly really, really enjoyable to do this proof, and I hope you guys felt the same way. And at the end of the day, I think that Furstenberg kind of tops Euclid with his proof that there are an infinite number of prime numbers. So thank you so much for watching.